ahead.
Okay, so any questions left over from previous two lectures?
I had one actually.
Please.
Is there any relation between ETH and that operator spreading you talked about?
Yeah. Well, more the operator spreading is the dynamical thing. I guess what ETH, ETH is basically saying that the eigenstates of the Hamiltonian are essentially random superpositions of all the states, in that part of the Hilbert space. And I think the implication there, the operator spreading is a more detailed thing telling you about the dynamics of how things happen, not just in eigenstates, but those operators spread and eventually they become pretty much random operators as well. And so there's a sort of an ETH for operators that the operators spread over the entire system, systems that thermalize, and they become essentially random operators, except they do have the same spectrum they had to start with. But so that's sort of a relation. It's a little vague, but maybe that's something.
Yeah, I was thinking, does ETH always imply that kind of spreading? It probably does usually.
Yeah. I think there's an ETH. Well, there's thermalization of operators, and you start an operator and run it, right? Right. You take the operator, its eigenstates are non-equilibrium states, and you run the operator, and those eigenstates become random thermal states, and so the operator, looks like a random operator. Of course, it's got a little bit of structure remaining in that its spectrum hasn't changed, and the system is local, so there's a few constraints. And precisely what those constraints are, as I said, that's in some sense the off-diagonal part of the ETH. There's still stuff there that we don't know exactly what correlations are there, what constraints are there. But the the best first approximation is the eigenstates are just random vectors in that part of the Hilbert space, and the operators just become random operators. Right? That's a good first approximation for systems that thermalize. But today, we're talking about systems that don't thermalize. Actually, we'll talk about systems that don't thermalize when the parameters are small, and when the interaction parameter gets big, they do thermalize, and there's a phase transition between them, right? Okay, so I talked about single particle Anderson localization and how that can be thought of as many-body localization, and now I'm gonna dive into many-body localization a little deeper, and I actually want to take my reference sort of non-interacting model and make it even simpler. So someone was objecting, oh, this Anderson localization is completely trivial. Well, today's is even more trivial. So start with an even more trivial non-interacting spin 1/2 chain. So my H naught is just some spins, spin 1/2s, whose Z components are coupled to fields, and the fields are different on each side. So this is just a bunch of independent spins, each processing about the field, and the fields along the Z axis. We have no degeneracies, just to keep things simple. The fields are all of order 1, let's say, and they could be random, or they could be some quasi-periodic pattern or something like that, non-random. So this has the same structure I was talking about yesterday. It's got a complete set of localized conserved operators, and now the operators are actually localized on one site, strictly localized. But we're going to relax that in a second. And so we have this structure, right? The operators commute with each other, and they commute with the Hamiltonian. Okay. Very simple. The eigenstates of this, of course, are spins up or down. Those eigenstates are not thermal, except for 2 of them, right? If these fields are all non-zero, this has a ground state, and the ground state is a thermal state because all the spins are in the ground state. And then there's the ground state of minus H naught, and that's all the spins are in the highest energy state. And that's the thermal state for that version of zero temperature. So these are zero temperature thermal states, but all the rest of the eigenstates don't look thermal because their energy corresponds to something that's non-zero temperature, but every spin is either up or down. It's not in a Boltzmann distribution, right? So they're not thermal. Okay, so that's the simple starting point. And now we're going to add some general nearest neighbor interaction. So we're doing a one-dimensional spin chain. We put nearest neighbor couplings between the spins. So here's H naught. I have some spin coupling spin in to spin n plus 1. It could be different from bond to bond. I'm assuming.
David, just to clarify, these are not along C. They are in any direction. Yes, these are operator, can be in any.
I was going to say, these interactions do flip the spins.
Okay.
So they have X and Y components in them. It could be a Heisenberg coupling, for example, but So it contains spin flip operators, the interaction. It's order 1. And then I have an interaction, G, coupling constant, which I'm going to adjust to go through the phase diagram. So when G is 0, we're many-body localized. When G gets large, it thermalizes, provided the interaction is sufficiently generic. And if you just pick random matrices for this, this is a 4-dimensional Hilbert space of these two spins. So these could just be random matrices in that 4-dimensional Hilbert space. That's a nice thing. And that by itself will thermalize. Okay. Now, right. So if we turn this on and G is small enough, the system remains MBL. And I'll say a little bit about how we understand that. That was shown perturbatively by Bosco, Alainer, Altschuler, argued perturbatively by Anderson. Of course, both Anderson and them were working with different models than this, but it's essentially the same argument. And then John Embry, who's a mathematical physicist, he wasn't able to do a full proof, but he was able to control most or many non-perturbative effects and show that in one dimension with short-range interactions, it still remains true, even non-perturbative. Okay, and how do we think about that? I was saying this a little bit at the end yesterday in response to Leo's question.
But David, but for the BAA paper, that's not just 1D, right? That's for 3D?
Yeah, right. So this argument here, Bosco, Alainer, Altschuler, so this doesn't have to be 1D, right? This could be all sites in some d-dimensional lattice, and this could be short-range couplings in that lattice, and their argument would be still fine. But then Embry's argument doesn't work, and then, as I'll hopefully say later, there's a good reason. We know one non-perturbative effect which destroys MBL in more than one dimension. So
sorry, David, that last interruption. So
they were doing any dimension perturbatively. He was doing one dimension, and we believe above one dimension there is a non-perturbative effect which destroys MBL as a true stable phase with the structure I was telling you.
And just last question. So the HNs they do have to be fully random in this case, or like last lecture that they can be anything, or the requirement.
Okay, so Embry was just doing the random case. The quasi-periodic case is technically much more difficult than the random case. And so nobody's really produced anything like what Embry did for the quasi-periodic problem.
Okay.
Although the numerics shows MBL is more stable for quasi-periodic than for random. But the mathematical physics is much more difficult.
Okay.
But there's no reason to think the quasi-periodic, if anything, the quasi-periodic is more stable than the random for reasons that I'll hopefully get to. Okay. So an understanding of, the understanding in terms of MBL being integrability, which I was telling you about, goes to these papers. So there's a paper, Serbin, Popic, Abanine 2013, and then we had a version sure. Ganessian. Vadim Oganessian is the one who got me started working on these problems, both in thermalization and in MBL. So what you do, as I was saying in response to Leo's question, you have a non-interacting problem. It's integrable. We add the interactions. Here we've got these conserved quantities, which are like particles, and we want to dress them to make them quasi-particles. And so basically the idea is dress, quotes, the Zn to make what we in this paper call L bits, localized bits. So they're pseudo spins. This is a spin. We make a pseudo spin. And that looks like this, just very schematically. Tau n is going to be Zn plus the dressing, which is going to include multi-site terms. And when this works, so for small enough g, I'll finish that thought later, for g less than some critical value, which is bigger than 0, you get the complete set of conserved quantity structure, complete set of this. And these multi-site terms decay exponentially with the range. So in that sense, these L-bit operators, which are the conserved quantities, they remain localized when we're in the NBL phase below some critical value. And the details of how you do this are not particularly instructive, so I'm not going to really show anything. And it's kind of like in Fermi liquid theory, where you take quasi-particles, you add interactions. Sorry, you take particles, you add interactions, you dress the particles to make quasi-particle operators, to make those quasi-particles as long-lived as possible. But there, you can't make them infinitely lived. They have a finite lifetime, even at zero temperature. Yeah, even at zero temperature. Whereas here, you can do it and make them infinite lifetime in the entire spectrum, not just near zero temperature, but in the entire spectrum.
Just a clarification question. So is G always positive, or it can be negative too?
Let's define G to be positive. Yeah.
Okay, cool. Thank you.
And this is a little bit technical.
When I'm saying these things here, yeah, I mean G is positive or 0. Yeah.
Okay, cool. Thank you.
This is a little technical, but do you need this to happen for every operator or almost all operators? Are you okay with one except? What do we expect is going on?
Well, what we expect is that they will typically decay exponentially. So some of these operators will have some resonance. So there will be rare cases where you might find an operator which is strongly mixed with something a certain distance away, right? But this happens with a probability which is exponentially small in the distance. So really it's the long range terms that get generated in the dressing typically decay exponentially with the range, and the probability that they don't decay and remain of order 1 is the probability is exponentially small in the range, right? And so it's not like they always decay. It's that they, you can have arbitrarily long terms generated that are of order 1, but this happens with a probability which is exponentially small in range. And that's the same situation with localized wave functions in Anderson localization, because you can have resonances that are special things that happen that make things sort of bilocalized, localized on 2 sites, things like this. So the operators are localized pretty much to the same degree as wave functions would be localized in single particle Anderson localization.
David, can I ask a question?
Yeah, please.
Yeah, so, when you talk about fermions or spin 1/2, qubits, then the size of the operator, these dressings, in Fock space, in a space of operators, is the same as the range in real space, just because, sigma squared is 1, or, c squared is 1. But when you have bosons, you could have a range in real space, but you could also have a range in, a dagger at site 1 to the 5th power or something like that. So I'm wondering if you could comment on, the distinction of those in terms of dressing. Or maybe things are not well defined for bosons.
No, this is an interesting question. People haven't looked that much at what happens when you're doing bosons and you have worries about going to quite large occupation numbers, because of course you can't do good numerics for that because the Hilbert space is too big. So,
Right.
So far there's no indication that MBL is any different for bosons or fermions or spins. Just small technical differences, but it hasn't been explored so thoroughly for, in the regime of bosons with large occupation number, just for
I see.
for practical reasons.
Okay.
So I won't insist there's nothing subtle and interesting there, but I'm not aware of it.
Okay.
Yeah.
Thank you.
Okay, so now I've sort of set out what a model looks like. And there's many different models that have been studied, but they generally look like what I'm saying here. They've got a limit where they're localized sort of trivially, and then you add some interactions, and those interactions, could thermalize it do thermalize it when the interactions get very strong. Sometimes it's presented the other way around. You start thermal, and then you add the random fields and localize it. But it's, that's just a matter of viewpoint. And the simple limit really is the localized limit. Thermalization isn't as simple as a bunch of independent spins in a field. That's much simpler than full thermalization, right? So I view the limit of the MBL phase as the simple limit. And then you go towards thermalization, which is not quite as simple, although we think we understand it pretty well. Okay, so what I want to do now is just show, actually I'm just going to erase and summarize what we think the phase diagram looks like for models like this. Okay, so these are now, I have to emphasize, these are dynamic phase diagrams. We're not talking about thermodynamics. This is the properties of a typical state of the system. Thermodynamically, it corresponds to infinite temperature, right? And if you have a one-dimensional system or an any-dimensional system at infinite temperature, the entropy is constant. There's nothing going on in the thermodynamics. But we're just looking at the dynamics, okay? And what that looks like, so first I'm gonna show it for 1D with short enough range interactions. And hopefully later I'll explain why we have to put those provisos on. And we're just going to have a one parameter phase diagram where we're just turning up the interactions, G. So this is 0. So here's the trivial case. And in one dimension, what we have, at least as far as we understand it, there's an MBL phase here, which I've told you about. I haven't told you everything about it, but I told you a fair amount about it already. MBL phase, phase transition, which is just in the dynamics. And then there's quite a bit further along, a crossover, which I'll show like this. So this is a crossover, meaning it's not a phase transition. There's nothing singular in the dynamics there. And okay, so over here is the thermal regime. And that means, okay, so this is, sorry, I should put this here. So this is for a given LT. So we're looking at a system of size L, and we're looking at time scale T. So we might have size L and we've exactly diagonalized it. So we looked all the way to infinite time. Or we might have an infinite system, but we're only looking out to a finite time. And that's sort of what the situation is in the experiments, where they can actually do pretty big systems, but they just can't run them for very long because of decoherence, external decoherence. They're not isolated enough. Or we might be somewhere in between because of a certain type of calculation that's being done. Okay. And under those circumstances, here, the system does actually, well, not fully thermalize, but it approaches thermalization. Right? There's always either small finite size effect or small finite time effects or such things, but you really see it does thermalize over here. Okay. Whoops, there goes the lights. Sorry. And then this crossover, this depends on the length scale and the time scale you're looking at, and goes to GC for L to infinity, T to infinity. But on the time scales and length scales you can access in numerics or experiments, it's actually a long ways away from the phase transition, like a factor of 2 or 3 larger interactions.
David, does the order of limits matter there? For the L and T going to
No, I
infinity?
don't think it's gonna matter. It's, yeah, exactly. Yeah, no, no, it's not gonna matter.
I have a question.
Right, because if you have a finite size system, there's some point at which it's too small to thermalize it. The bath that it would have made if it was bigger is too sparse, and it can't thermalize such a small system because there's really no bath, right? But that will go to the transition in the limit, and then similarly, if you only wait a finite amount of time, it won't be able to approach thermalization, even if your system is very large. Yeah, go ahead with the other question.
Yeah. So let's say like I am doing numerics on a system and trying to find whether it has an MBL phase. And since it's numerics, I can do only finite size system. In this case, is it legit to say that I am probing the transition, or should I stick with crossover?
You're looking at this.
Mm-hmm. Okay.
So, and if you read the literature, almost everybody doing numerics is studying this, but they're calling it usually the phase transition.
Yes.
Right. Whereas I'm saying that's the phase transition is over here. And what they're studying is a crossover between this regime and this regime here, which I'm going to today, the language for this is not established. I'm going to call this pre-thermal MBL regime.
Then if I want to be strictly correct, I should be calling this crossover in like any numerical study, right? Not a transition.
Well, most numerical studies. I can, we have just yesterday posted a paper where we devised a way of doing numerics that really is focused on trying to locate this more directly than other methods. So I think numerics that are focused on here rather than over here are possible, and we've made an attempt in that direction. I can tell you about that later. So this
also, if you can get the crossover.
This is the transition in the limit L to infinity time to infinity. That's where
I don't see how you, if you're talking about finite L and finite T, then it's all MBL, strictly speaking. Well, I mean, it's all one phase. It's all one phase, if you wish. There's no transition.
Well, this is for given L and T. Yes, this is not visible. Right. Let me just finish what I'm saying here. So this is a point I'm marking on here. You won't be able to see it cleanly for a finite L and T, within finite T. But if you could, in principle, take these limits, this is where you would find the transition to be. And as I say, this is not directly visible, directly seen in numerics or experiments. What you see in the numerics experiments is this stuff over here. Okay. Now, I was going to.
David, there's a question in the chat from Yicheng Zhang, who asks, "What's in between the crossover and GC? Is it finite?"
Yeah, well, you guys aren't giving me time to say that. That's just about what I'm going to say. Okay.
I have a maybe stupid question.
Should I just say that before any more questions?
Go ahead.
Okay, I started saying it. It's the pre-thermal MBL regime. And so this appears on these scales, appears MBL, but thermalizes in the limit L to infinity, T to infinity. So this and this are the thermal phase. This is the part of the thermal phase which at these scales looks like the many-body localized phase. And this is where it's switching over between those, right? And roughly speaking, and that's part of the current research, is to ask, is what I'm about to say something that we can make more precise? Here, MBL is perturbatively stable, but non-perturbatively unstable. So if you look in Bosco, Elaine, or Altshuler, where they just do perturbation theory, they estimate where the transition is, and you get an estimate which is over here. Okay, so that's sort of the quick summary of this landscape. And I guess in some sense it's not necessarily a phase diagram, because this distinction here isn't a phase transition. It's a crossover. It's smooth, but it's quite striking in the numerics and the experiments. It looks a lot like a phase transition. Okay, now I just want to, so this is 1D with short enough range interactions. And then if we do longer range interactions, or D bigger than 1, what we expect is the non-perturbative instabilities become stronger, the critical point goes to 0. So there's really no MBL phase at a non-zero value of G in the limit. And so this phase diagram just simplifies to just having this regime, the crossover, and this regime. So it just pre-thermal MBL crossover and thermal.
David, and I think you were going to say, but there is a specific criteria to distinguish pre-thermal to thermal, or you're going to tell us that?
He just did, I think.
Yeah. Well,
more specific, like very.
Here, I'll say a couple of those. So one is you look at the eigens. If you say do exact eigenizations at finite L, over here the eigenstates are obeying ETH, and that's getting better and better as you go to larger system sizes. Whereas over here, the eigenstates look localized, they're very far from ETH. Low entanglement, volume law entanglement.
But that maybe my question is more generic.
Start the system in a non-equilibrium state, it stays localized near the state over here. It will stay localized near the initial state you gave it, whereas over here, it will relax to thermal equilibrium on the time scales you have available, or in the finite size systems you can do.
So maybe my question is in numerics.
Yeah, go ahead, sorry.
In numerics, you need to access then all the eigenstates to describe. So if you try to extend, for example, some other numerical methods that don't give you the full eigenstate, but give you certain observables, then it's going to be hard to distinguish pre-thermal to thermal, yes? Or
No. First of all, you don't need all the eigenstates because all the eigenstates pretty much behave the same. So if you're doing some, shift invert or something where you can just get a couple, 10 eigenstates in the middle of the spectrum and you can't get them all, that's good. That's good enough. And people do that. So you don't really need all the eigenstates. And then there's dynamical methods where you don't get eigenstates at all. You just take an initial state and time evolve it.
Yes, exactly. That's my question.
An experiment, and you can just monitor observables, right? You can start with, say, in cold atoms, people like to start with this thing where the odd sites are occupied and the even sites are empty, right? What do they call it? The imbalance between the odd and even sublattice, and then just ask if the system thermalizes, those densities will become equal on the even and odd sublattice, and if the system is localized, it won't, right? And that's a very simple observable, and if you have a method which either an experiment or a numerical method which does the time evolution to some precision, then you can do that, right? And you can ask on a given time scale, where is this crossover, right? Here, it remembers the initial condition strongly. Here, it's pretty much relaxed away. So
can you
lots of methods that allow to see this.
Okay.
Can you also distinguish more sharply? Can you distinguish the two by asking what the equilibration time, how the equilibration time depends on G, or maybe system size?
No, that so far has not proven to be particularly useful.
Well, but you're saying that the pre-thermalized state or regime, it's non-perturbative in G. To recognize that it's thermal.
But this is sort of
asymptotic.
this is my conjecture. These are not statements that you can actually use to analyze such data.
Oh, I see. It's not like
this is a vague theoretical idea of what's going on.
Right. I was thinking it's more like in a Costello-Stalla's phase diagram.
You have ideas of how the relaxation time diverges as you approach this, right?
Okay.
But that's a regime where they're so big that you can never measure them anyways, either in numerics or in experiment. So it's just not an accessible regime, the Costello-Stalla's behavior that we think happens around there. That's just like, it's not.
No. What I meant is, in a Costello-Stalla's flow, if you're at zero fugacity, there's a phase transition pi/2. But if you at some critical value, but if you're finite fugacity, even in the regime, you first flow down and then you start flowing up in the unstable regime. So when you're flowing down, you would think, it appears like you're.
Yeah, you're bringing up Kosterlitz Thales. Okay, so there was this paper way back in the day, which by Bishop and Reppy, right? And they looked at exactly the kind of stuff you're talking about in the experiment, and it looked like this. Now this wasn't enormously far from this, but it definitely looked like this, right? The transition was over here. All the action in the experiment happened over here on this side of the transition. They had an elaborate theory to fit all that, and it was consistent, right?
Okay.
We don't have enough details to do that.
Okay, good.
Right?
Okay, thank you. That clarifies it.
Yeah. So actually, that's what I was going to say next. So we've got this crossover. So we have understandings of thermalization that we think are pretty good out here, well away from the crossover, which I've been telling you about. And we actually have, we think we have good understanding of the MBL phase and maybe even this transition, but that only applies at enormous length scales and enormous time scales, which are inaccessible. But this region here, which we can get at in numerics and experiments, we don't really have great theories for yet. So I guess maybe I should say not much theory of this yet. Now there is one page there. Yeah. So there's a nice paper I like. Bill Crowley and Anushka Chandran have recently made some effort developing some theoretical ideas about this, which are not trying to fit it into the box of a phase transition, but to really think of it as a crossover. And so that's, let me just give the reference on that one. So this is quite recent, 23. And we've been exploring this regime here as a pre-thermal regime, and I'll tell you a little bit about that. And that's the paper we just posted yesterday.
David, is that Chandran reference 2021?
2012.
Okay.
Year 20. This is not a year. This is an archive. Sorry, this is an archive number.
Gotcha.
Year 20, month 12.
Yeah.
Right? You see what I mean?
Yep.
Yeah, that's always confusing. Yeah, so we published in the future, 2107, or posted. So that was posted, that was posted yesterday. So this is Morningstar and a few other people and me. Morningstar, Colmenares, Kamani, Lewitz, and Huse. Okay, and these papers, one of the things these focus on is what I'm going to tell you about next, which is many body resonances. Okay, so how am I doing? Whoops. That's what I do when it's not COVID. Have to erase. Yeah, so that's sort of a summary, and I want to say a little bit more in particular about the less well understood parts of that phase diagram. Okay, so my theme is instabilities of MBL. And this could be the MBL phase or the MBL regime going unstable as we get to that crossover. And MBL is a type of coherence. Long-lived, we could call them excitations, or yeah, I'll just call them excitations. Long-lived operators, long-lived conserved quantities, or infinite-lived if we're actually in the NBL phase. Whereas thermalization is decoherence. So NBL is quantum coherence, thermalization is decoherence. And we know,
Sorry, can I ask you a question?
we know who wins this battle. When you have decoherence fighting with coherence, the decoherence really has the upper hand, right? You know, it's like, this is destruction, this is organization, right? And when you have a few people organizing something and the same number of people destroying things with weapons, you know what's going to happen, right? So thermalization really has the upper hand in the battle between thermalization and NBL in this phase diagram we're talking about.
So I think there was
somebody wanted to ask something.
Yeah, I was actually going to ask a question regarding the phase diagram. So in the NBL phase, you expect almost all of your eigenstates to have, you know, a certain property. I mean, something like area law. So in this transition or the crossover for finite systems, do you expect the property to be lost for, you know, all eigenstates at once, or do you expect some of them to?
No, there's a distribution. We've looked at those things. You know, that's the kind of thing that, you know, there's definitely probability distributions where different. I lost my pinning. Different eigenstates are doing different things, and also different samples are doing different things. So if you draw different samples, say with random fields, they are doing different things. And so yeah, as you go, particularly, you know, through that crossover, you get very broad probability distributions of the behavior, both sample to sample differences as well as differences within a sample between eigenstates. Yeah, I have a paper with Vedika Kamani and Donna Sheng exploring some of that stuff, a couple of papers.
I see. Do you expect the transition to actually get narrower as you make the system larger, let's say? Do you expect the eigenstates to actually?
The things sharpen up on the phase diagram, the crossover sharpens up, yeah. Some distributions of quantities actually get broader as you go to larger systems, because as you go to larger systems, the system is renormalizing to stronger and stronger randomness. And so the probability distributions of some quantities actually get broader as you go to larger systems. And that's what we demonstrated in some of our numerics. Okay, so because of this, you know, NBL being coherence, it's fragile, right? Any quantum experimentalist knows that coherence is fragile and decoherence is powerful and usually wins. So that's why we view this as instabilities of NBL, because NBL is fragile, and we want to ask, can it survive or does it go unstable? Right? Thermalization is robust, right? And so looking at this as an instability of thermalization towards localization so far has not been productive. Now, maybe there's some ways to make that a productive viewpoint, but it hasn't been so far. Okay. So, and there's two types of instabilities I want to say something about, one of which is more relevant to the crossover. And I wanted to do that one first because that's actually the thing which is much more observable. And this is many-body resonances. So I want to say a little bit about many-body resonances. Okay, so say we're in either the NBL phase or the pre-thermal NBL regime. And so we have all or almost all eigenstates localized near one spin configuration. Now, how many eigenstates do we have? We have a chain of length L, spin a half, so we have 2 to the L states. So if we take 2 states that are adjacent in energy, the difference, energy difference, is of order 2 to the minus L. So if I diagonalize an MBL system, completely diagonalizing, I get 2 to the L eigenstates. They're spread over an energy range that's of order 1, maybe of order square root of L, but not exponential in L. So the typical level spacing between the eigenstates is 2 to the minus L. You know, maybe with some polynomial in L factors, but it's exponential in L. And these 2 eigenstates that are adjacent in energy, they're adjacent in energy really just by coincidence, right? The fields on the spins just happen to add up to almost exactly the same energy. And so let's say alpha, I'm going to call these 2 eigenstates alpha and beta. They're adjacent in energy, and they're localized near a particular spin configuration, and they differ on of order L over 2 spins. So one of them might be localized on a spin configuration, say up, up, down, down, up, up. And then the next one, you know, this spin might agree, this one's flipped, this one's flipped, this one agrees, this one agrees, this one's flipped, this one's flipped, this one agrees, right? So they differ here and they differ here. So actually this is atypical. I've got the differences, you know, I just drew some spin configurations off the top of my head, but the idea, you know, they don't necessarily come in groups of 2, the ones which are flipped. That's just what I happen to draw. So this would be alpha, and this would be beta. And in energy, what we've got is, here's E alpha, and here's E, let's put it straight below it, here's E beta, and this is of order 2 to the minus L. Okay. Now, in MBL, we have these conservation laws, sorry. And, you know, if you have conservation laws due to really good symmetries like angular momentum, associated with those conservation laws, you get good quantum numbers and selection rules. And so if one eigenstate is angular momentum 0 and another eigenstate is angular momentum 1, and angular momentum really is conserved, then the Hamiltonian will not mix these 2 states. There's nothing in the Hamiltonian that will connect this state to this state, and they could be exactly degenerate, and that's just an accidental degeneracy. But the conservation laws that show up in MBL, these localized conserved operators, they're not like that. They're emergent in some sense. They're very specific to that particular Hamiltonian. If you change to a different Hamiltonian, the conservation laws are totally different ones. The dressing is totally different. And as a result, we don't have any selection rules or good quantum numbers associated with our conservation laws. Okay? So H does couple these 2 states, alpha and beta. Thinking perturbatively in the interaction, I've got to flip to get from state alpha to state beta. I've got to flip L over 2 spins. And if my Hamiltonian only has, say, 2 spin terms in it, that's going to require going to an order in perturbation theory, which is of order L. Right? So the Hamiltonian does couple these, but only at an order which is of order L. And this will produce level repulsion and hybridization, meaning linear superposition between these two states. And it's happening at order L. So what we find, or well, you just argued, you have a weak interaction. It's producing a coupling between these two states at Lth order in perturbation theory. That coupling is going to be exponentially small in L. Because when you do perturbation theory at each order, things are one factor of the coupling constant smaller, right? So what you're going to have is, this is so the typical level repulsion. So one point is, even if you're deep in the MBL phase where MBL is stable, the eigenstates still show level repulsion. It's just weak, right? It's not strong enough to produce random matrix level statistics, but it's there and it's just weak, right? And if you go in there in the diagonalization and look, it's there. You can calculate it, and we've done that. So the typical level repulsion is going to be exponentially small in L. Now, it's not going to be just G to the L, right? Because you only have to flip L over 2 spins, and you might be able to sometimes flip 2 spins with one term in the Hamiltonian. So it's going to be something like, so the level repulsion, it's going to be exponential in L, but I'm going to write it like this. So there's some number bigger than 1, which is put to the minus L. It's a function of G. It's some power of G. So this is exponentially small in G to L over some number. Right? So K, K versus G, it's something like this, approximately a power law. As G goes to 0, there's no level repulsion, and that corresponds to K going to infinity. Okay. So this is an argument that for a system of length L in the NBL regime, the level repulsion between adjacent eigenstates, which is producing level repulsion as well as producing hybridization between those configurations, is exponentially small in F with some thing that behaves qualitatively like this. Does that make some sense?
Can I ask?
It's heuristic, but we've tested this kind of stuff. It's roughly correct to the numerics. Yeah.
Can one use this prescription to define the transition as the point where this K of G is exactly 1? Is that a meaningful way?
But you're close to what I want to say next. That's not precisely what I want to say, but it's close. Okay, so remember the typical energy difference between the adjacent states is 2 to the minus L, right? So as soon as this becomes of order 2 to the minus L, that is strong level repulsion and strong hybridization between those eigenstates. And so roughly speaking, the crossover, so the crossover from pre-thermal MBL to thermal, that crossover happens when K of G is about 2, not 1, 2. So you were close. But that's the crossover. That's not the transition. That's the crossover, right? So once this becomes 2, then every pair of adjacent eigenstates are strongly coupled to each other and they're going to mix, right? And that's the beginnings of thermalization. Is now the eigenstates are much more complicated. They're not localized on just one configuration, right?
David?
But when this is bigger than 2, then as we go to a large system, this coupling between the adjacent eigenstates is much smaller than the energy difference, and most eigenstates will not be involved in such resonances. So we call it a resonance when the level repulsion, the coupling between the 2 eigenstates, is comparable to their energy difference. So they really form substantial linear combinations when you diagonalize it. And that's what we mean by a many-body resonance.
So David, am I right that if I had some symmetries, magnetization was conserved or something, that basically this would all still be true, except maybe that K of G value would change to 3 or 1.5 or something, shift value?
Well, actually, like if you put in, we did look at the standard model of MBL, which is conserved total SZ, and all that does is modify these things by power laws. The exponential, right? The thing is, if you have a fixed total spin, but you have a chain of length L in a given spin specter, you still have an exponential number of states in L. It's still 2 to the L, but it's going to be divided by L to some power, right? And so all that does is modify with power laws, but the exponentials are really unaffected by those conservation laws.
David, G is your interaction as you defined it, but is it measured in units of the strength of disorder somehow?
Yeah. I said the fields on the sites were of order 1. I'm working in units where at G equals 0, my spins are in fields which are of order 1.
Okay, thank you.
That's right. Okay, so this is where the crossover happens. But really, as with everything in MBL, there are strong finite size effects. And instead of K of G to the minus L, it should be K of G and L to the minus L. There is a dependence on L, more so than just the exponential. And then K versus L also decreases. So as you go to larger L, with larger systems, it's, at least in terms of the sign of the effect, like going to stronger interactions. The thermalization gets stronger as you go to larger systems at fixed G. So that's why the crossover would happen when K of G and L is of order 2. And then since this drifts with L, the G at which it happens will drift with L. And precisely what is the main mechanism in the part of the phase diagram that you can actually study numerically behind this dependence on L, that's still obscure. So it's, that's a numerical observation, but the underlying mechanism, I would say, is still not clear to us. And then, so what we call many-body resonances are eigenstates that are substantial linear combinations of very different spin patterns. So when you have an eigenstate that contains a substantial amplitude for 2 very different spin patterns, that's what we mean by a many-body resonance. It's different over the whole system, And there are sort of two limiting cases of that. These are always present in the NBL phase, but they're very rare deep in the NBL phase, and then they become common as you approach the crossover. So these could be, if there's only two patterns, like I was talking about, then the eigenstates can look something like this. Plus minus beta, and these are cat-like. It's just a resonance between two eigenstates, which happen to be almost degenerate, much more so than typical, and then the actual eigenstates are admixtures like this, and these are very different spin patterns. This happens. You can find these, and they occur. They're rare, but they occur in the NBL phase and in the pre-thermal NBL regime. And then if it's many patterns, that's really what thermal states are. That's how you get to a thermal state, is you make a linear combination of many different patterns. And you know, that's what the thermal state looks like.
But how do you distinguish pre-thermal from NBL?
That's the next topic.
Okay.
Any other
Thank you.
questions? Okay, so yeah, I'll summarize. Yeah, I still have 20 minutes, so I think I'm doing okay. I'll just jump to the summary when I run out of time and get back to this, put this in the context. But any other, so this is a little bit about what I mean by many body resonances. And if you look in our paper that we just posted, we've been studying them and quantifying how many of them there are in different parts of the phase diagram and identifying various features associated with that.
So David, going back to this question about symmetries and the counting, so I believe everything you say for global symmetries, but there are, like, you know, gauge symmetries or these subsystem symmetries and fracton models. Could those change all the counting and localize in different ways?
Certainly, certainly.
Has this been studied?
Well, you know, there's fragmentation. Yeah, that's like a whole. Yeah, you're right.
Well, yeah.
But I'm not going to talk about it.
But is this in like the review articles that people have written that I could dig into this, or is this just things?
Well, all that stuff is so new that, yeah, I don't know. I don't know that anybody's really made an effort yet to put fractons together with NBL in a really organized way, but I'm not sure.
What about just ordinary gauge theories?
Yeah, I don't know.
There are no symmetries there. That's degenerate. That's redundancy. So
my approach in these problems is stay away from symmetries. The symmetry, you know, the essence of thermalization and the essence of many body localization has nothing to do with any symmetries except unitarity, and the symmetries just make it more complicated, right? And we don't even understand the simplest case very well. So my inclination is to stay away from that stuff. But yeah, other authors explore those things. But yeah, sorry to be not cooperative to that line of questioning, but I'm just being honest.
Sorry, question?
Yeah, go ahead.
You know, when there's this kind of resonance, there's this kind of instability of the NBL phase.
Well, the many body resonances, just having one of those in the spectrum, that's not really an instability of the phase. That's just a peculiar eigenstate, but it doesn't destabilize the phase. It's really only when almost every eigenstate is involved, then you start seeing more like random matrix level statistics rather than Poisson level statistics, right? And so, yeah.
So yeah, I was
It's the
going to,
proliferation of these resonances that is the instability, not single ones. There are single resonances happening deep in the MBL phase, and the MBL phase is stable to them.
I see. So I was going to ask whether, if you think about, the L bits and, a perturbation expansion for the L bits, you expect these contributions to actually be very small, as you said, order L in the perturbation. So your L bits should still look like, before. Does perturbation theory break down at this point that, you start to have thermalization?
No, I don't. No, I think you can have these resonances present and they contribute to the L bits. So, you have a sample, it's got 2 to the L eigenstates, and let's say 5 of them are strong many-body resonances, right? But that's a fraction 2 to the minus L of the eigenstates. And the amount of weight they have in a typical L bit operator is exponentially small, right? And so they don't destroy the localization of that L bit operator, they just contribute to the exponentially small tail that it has. So the L bit operator has a tail out to large distances, which is exponentially small. And that's contributed by eigenstates that have long range structures. So I think there's no, initially when I realized these resonances are there, I was worried, oh, that's going to destroy the L bits. But I don't think it's a problem as long as they're rare. It's just a measure 0 fraction of all the eigenstates in the limit of large L. Okay, let me continue with the last topic. So the other known studied instability of NBL. So this was a perturbative discussion, right? I just talked about it perturbatively. This one is non-perturbative, and this is what's called the avalanche. And this is due to Rydberg. 17. And this is for random systems. So if you have a random system, the local conditions, the local fields, the local couplings are random, and you can just by chance, those random numbers could come up with a jackpot such that although we're in the NBL phase, this particular little patch of my sample got fields that were almost all the same with lots of resonance, lots of degeneracy or almost degeneracy and very strong interactions. And so it thermalizes, right? So we have a picture that looks like this. Here's my sample, and I'm actually going to leave one dimension for the picture right now. So here's my sample, and here's a patch. And in here are N spins. And this region here locally is thermal. And it's just by chance. So these are rare, but they exist, right? You just happen to draw random numbers here that made a system which was quantum chaotic and locally thermalized, but then everywhere else it's NBL. And so this is all typical stuff, it's NBL. So we're in the NBL phase, but no matter where we are in the NBL phase or the NBL regime, you're going to have these patches that locally try to thermalize just because by chance the Hamiltonian there is locally quantum chaotic, whereas over here it isn't. Okay. And now let me continue at the top here.
And David, are more pronounced in higher dimensions, or these are, what is the difference?
It's more of a problem in higher dimension, it's a more potent instability in higher dimensions, as I'll show you. Okay, so the way I like to discuss this is this way. So one, turn off all couplings between our let me call this the core. And I'll call this the rest. So the core is the spins in this region which locally thermalizes, and the rest is all the other places which would be MBL if it weren't for this core here trying to thermalize them. So between core and rest. So now it's two decoupled systems, and then we diagonalize. So the core, we get thermal eigenstates, highly entangled, quite random looking. And in the rest, we get L bits, well localized. They get dressed, and then H does not flip L bits. So the L bits are conserved. So if I cut all these bonds from the core, I get L bits out here and they're conserved. No flips. Okay? And so the eigenstates of the combined systems are just products of eigenstates of the core and eigenstates of the rest. And in the rest, it's just spins L bits up or down. And in the core, it's just some random looking thermal state. Okay? So that's the first thing we do. And now we do it, now we turn on the couplings. And think about this. And the question is, does this small bath, right? This core here is trying to be a thermal bath. Does this small bath get entangled with and thermalize the L bits? That's the question. And in order to do that, it's got to flip them because we want to relax. You know, they're polarized. Some are up or some are down in the initial state. And the thermal state, they would all be randomly up or down. So you've got to flip them to thermalize them. Okay. So let's start this. So let's think of an L bit very close. So so the bath has n spins. So the bath, in quotes, the putative bath, has a level spacing 2 to the minus n, right? Because there's 2 to the n eigenstates there, and the same argument as before. So the bath has level spacing 2 to the minus n, and then the coupling to the closest L bit, adjacent, closest in space L bit, bits, all the ones which are immediately outside of it, is G, whatever G is, right? Because G was the coupling. I turned it off and then I turned it back on. Okay. Now, clearly, if n is large enough, right? And for a random system in the thermodynamic limit of an infinite system, if I look around, I will find such cores of all sizes. They're exponentially improbable in their size, because in order for it to happen, I had to have everything do just the right thing there, but they're there with some non-zero density. So if n is large enough, clearly 2 to the minus n is much less than G, right? If G is some finite number, I can certainly find an n such that this is true. And then the bath looks like a continuum to the spin, the L bit that's right next to it, and it will have processes which get it entangled and it'll thermalize. So the point is the close L bits do thermalize. And this is the start of the avalanche. And I'll say why we call it an avalanche. It has some features of an avalanche that once it gets going, it's more likely to continue. But it has other feature of an avalanche that the farther it goes, the slower it goes, which is really not like an avalanche, right? This avalanche really slows down as it goes along. Okay, so that's right. And so now let's do the following. So shouldn't have erased. So here's my core. And now let's say the avalanche has gone to distance r. And I have an L bit out here that's at distance r from the closest part of the core. Now remember, absent the couplings to the core, this L bit is conserved. It never flips. So the only way it flips is by interacting with the core. Even if all these L bits out here get thermalized, they can't flip it, right? Because this was diagonalized and this L bit interacting with this L bit, there's no spin flip term, right? There's only a spin flip term when we turn back on these couplings to the core, right? And so this guy is only coupled to the core exponentially weakly in R, okay? So an L bit at distance r will relax with rate, we'll call it gamma, and I want to put in some factors of 2, so gamma of r, which I'm going to, so because of all the factors of 2, we don't use e to the minus, we use 2 to the minus. So we put 2's instead of e's. And I put a couple of 2's in here. So here's a decay length of this coupling. I've chosen to write it with 2's here rather than e to the minus r. That's a zeta, that's the decay length. And this is true if the bath is big enough. If this is a large bath, and I have an L bit here coupling to the bath through an MBL region, it will have a lifetime due to this bath, which will go to a constant when the bath becomes very large, because it's really just coupling to some operator right here. Right? And that has some weight, some magnitude of coupling. We could just think of this as sort of an open Lindblad system where we just, it's an open system coupled to a big bath over here. Okay, so that's the assumption, and that appears to be true, and that's some of the numerics we've done. We've taken spin chains, MBL spin chains with open ends, and then we couple the first spin in the chain to an infinite bath, either Lindbladian or we have a Floquet version of it. And then we ask, what's the relaxation rate of the farthest spin? This is actually a nice way to find the farthest L bit. You couple the spin chain to this bath, diagonalize that super operator, find the gap to the first, quote, excited state, the slowest state of the super operator. And that state, which is an operator, is the L bit at the farthest end, because that's going to be the slowest thing to relax to this bath. And so that's in our paper that was posted yesterday. Okay, got to speed up.
Isn't R time dependent? I thought the core would grow.
Yes. Now R doesn't change because this L bit only flips due to interaction with the core, right? And so although the avalanche is approaching it, that doesn't speed up its relaxation rate, because it's not relaxing due to interactions with the other L bits, because those are all on the diagonal, right? So whether the other L bits have flipped or not, that doesn't flip this L bit. It doesn't help flip this L bit. Okay, so we're going to let the avalanche proceed to distance r, and now let me right. So the avalanche has proceeded to distance r. So now the bath has, and I'm going to write a formula, and you can think about it, and it kind of makes sense. So in d dimensions, the radius of this core is n to the 1 over d if you assume it's compact, and then we add to that the distance. There's some coefficient here, and put this to d. That's how many spins. So when the core thermalizes an L bit, it joins the bath and becomes part of it. And so now the bath has more spins in it, and it's got a smaller level space. So it has this many spins. So this is in general. And then in 1D, the bath is n spins. It avalanches r to the right and r to the left. So it's n plus 2r spins in 1D. So I have the core is n spins, avalanche goes r to the right, r to the left. Okay, so this is 1D, this is general. And you see this is we put in d equals 1, a is 2. This a depends on d. Right? It's just having to do with the volume of spheres. Okay, so now the bath's level spacing is 2 to this number. Let me just do the 1D case. 2 to the minus n plus 2r in parentheses. So this is the 1D case. And we want to compare that to this, right? If the relaxation time, if the relaxation rate of the spin is much larger than the level spacing of the bath, then the bath looks like a continuum, and that's when this result is valid and the spin does get entangled with it and relaxes. That's Fermi golden rule kind of situation, right? Whereas once the estimated relaxation rate becomes small compared to the level spacing of the bath, then the bath is no longer a bath, because if the spin tries to flip and go to another, put the bath in another state, the bath can't take the right amount of energy because it's off shell, right? So the avalanche will stop when this becomes equal to this. And in 1 dimension, you can see that's when zeta equals 1, right? If zeta is bigger than 1, right? So this one starts off bigger, right? This is the level space, smaller, sorry. This is the level spacing of the bath. And at r equals 0, it starts off smaller, and so the avalanche goes, right? And then this is going down as minus 2r, 2 to the minus 2r, whereas this is going as 2 to the minus 2r over zeta. If zeta is bigger than 1, this one never catches up to this one. This is always smaller than this, and the avalanche never stops. And that's what happens in the pre-thermal MBL regime. An avalanche will just thermalize the whole system very slowly, right? The amount of time it takes to thermalize out to length scale r is exponentially long in r, right? So it's a very slow process, but it ultimately thermalizes. And so in 1D, the critical point is when this is 1. Okay, so that's in 1D. Now, if we go to more than 1D, this is decaying exponentially in r, whereas this, now, we get a level spacing 2 to the minus n to the 1 over d plus a r to the d. It's decaying exponentially in r to the d. And if d is bigger than 1, this is decaying faster than this. And so the bath, if we start off with a large enough n, the bath will always look like a continuum to the spin, and the avalanche will never stop. So this argument says that for d bigger than 1, if you start with a big enough core, the avalanche will never stop and the system thermalizes, independent of what zeta is. You just, if zeta is very small, you just have to start with a bigger core. Those are very improbable, but they occur with some non-zero probability. So this is the argument. Sorry to rush through it, but I'm pretty much out of time. I can sort of, what I was going to do is put up the phase diagram again and annotate it with the conclusions. But maybe before I do that, are there any quick questions about this that I just rushed through?
Yeah, I have a question. So you mentioned that the core happens by chance, but I'm just thinking about these experiments from Christian Grass, where what they do is
they put them in on purpose. Yeah.
That you change the bat system and then you see what's going on. So
right. Of course, in a quantum gas microscope, you can just put in the core wherever you want it to be. And they've done that, yes. And I think you'll hear, I think Emmanuel Bloch's going to lecture. You might hear about those experiments when he comes. Yeah. No, I'm discussing the random case, not the engineered case. But these ideas inspired those experiments, of course. Yeah, good point. Anybody else?
Can I ask a couple of questions?
Yeah.
One of them is, it seems like one of the fundamental things here is the randomness. So do we expect avalanche to also exist in the quasi-periodic regime, or sort of a regime where randomness kind of like has correlations to prevent?
We used to think not, that there'd be nothing to get the avalanche started, and so the transition in the quasi-periodic case would be some other mechanism. But then recently, Roman Vasseur and student and Sarangopala-Krishnan, they were exploring this, and there seems to be some instability happening. You know, what's happening in MBL in quasi-periodic case, well, it's not clear what's going on, but it looks like the quasi-periodic case is doing something rather similar, and it's having some instability. So maybe there's some way to get this started without the core. The core may not be necessary to get this started. Right? So it might be an instability that's always there lurking. But this is really unclear. That's a big open question. Is, you know, what is the first instability of MBL in quasi-periodic systems? How does it go?
And another question, like, in this argument, we kind of assume that every time one extra spin gets added fully to the path. Is there any way that, for example, there's fluctuations in how an efficiency, a random efficiency of how one L bit gets absorbed into the path?
Yeah, that certainly does happen. That the ones which are near the avalanche front, some of them will be in and some of them will be out. You know, and we've looked at that. The couplings, you know, these couplings I'm talking about here. You know, this is a typical value, but they have very broad probability distributions. Yeah, but that doesn't look like it would ruin the argument. It would just quantitatively change things a bit.
Okay, thank you.
But yeah, no, these are you know, all this stuff. More needs to be done to look at. In particular, you know, the story I told you ignored the fact that, you know, I was just talking about typical values of things, right? Where there are probability distributions, and the probability distributions are enormously broad. And you know, how does this change things? And that's something, yeah, people are beginning to explore. Yeah, we have a little bit of that in the paper that was just posted. Okay, so I'm just going to put back up this phase diagram and annotate it with sort of a summary. So here's the crossover. See. Okay, so this, in our present level of understanding for the random problems, and this is 1D, this is the avalanche instability. And we have a renormalization group treatment of this in various approximations, which you know, is interesting, Kosterlitz-Thallis-like, but a lot of, you know, uncontrolled assumptions. Okay, so here we have this pre-thermal MBL. here there are the many body resonances remain rare. So they're there all through the MBL phase, but they're rare. But the system is unstable ultimately to the avalanche in here. But if we're looking at a particular L, the system is too small to have undergone that instability yet. What else was I going to say about this? Yeah. So ultimately it'll thermalize due to this mechanism, or maybe there's some other instability that's more important up here than the avalanche, right? You know, that's one of the things. You know, there's a big difference here, and it may be the instability, the ultimate instability up here isn't really by the avalanche mechanism, but by some other mechanism, and that's not clear. Here's the crossover. Said that thermal things. Thermal regime, let's say, and this. The location of this depends on L and T in a way that we don't fully understand. This is far enough away from the avalanche that we don't know how to, you know, the avalanche may not be, which we have some theory of, it may not be at all relevant over here, and how all this stuff around here scales may be a rather different story. And that's just not clear right now. Okay, I think right. And as I said, you go to dimension bigger than 1 or longer range interactions. This part just disappears, but this part of the diagram remains. So you can do experiments on MBL in 2 dimensions and see this crossover, and there's a lot changing. So it's not that, you know, it's not a phase transition, but it's physics, and there's a lot going on. Okay. So that's sort of a summary of what I said. I think I've gone a certain amount over time, so I think I'll stop and open for more questions. And I'll show up tomorrow at the end of week session.
Oh, thank you. That's perfect. Thank you, David. That would be great. Yeah.
People want to bring questions from me there.
So David, you talked about Embry as proof, and you said he has some things under control, non-perturbative effects, and some but not all. But yeah, here you discussed two or at least one non-perturbative, namely the avalanche.
Yeah, the avalanche.
So what I'm wondering is, what is, you know, other mechanisms that maybe create additional crossovers or additional sort of worries that you have not discussed, just for the record? Like,
no,
you focused on 2.
I don't think there's anything that's been well formulated of other non-perturbative instabilities. You know, he was just doing a proof and he would bound things. So
I see.
You know, and it
but
wasn't.
Does he deal with these?
It wasn't really, you know, specifically indicating a mechanism, right? You know, and it's typical mathematical physics proof where you bound it and the bound probably isn't at all tight. So it didn't really indicate, at least to my knowledge. You know, in fact, when I initially saw it, he said, "Oh, I can only do this in 1 dimension." I said, "Oh, that's probably just some technical thing. You can only do 1 dimension." You know, and he didn't really have, you know, a clear insight of why it would be only 1 dimension. But then the avalanche story got elaborated, and oh, maybe there really is a reason you could only do it in 1 dimension, because in more than 1 dimension, there is no MBL that's truly stable. So, yeah.
So, I mean, but the summary is that
that's something that, you know, like I was just saying, there might be some other instability that's more important to the physics up in this region than this one, right? And that might help with understanding it better. But, you know, I don't know.
But the
So you talked
resonances that you discussed, you expect to behave similarly in pre-thermalized and MBLA states. You know, there's no qualitative change.
Just get more and more rare. They just continuously get more and more rare as you go deeper and deeper. Yes.
Okay. So the transition that's indicated is really set by avalanches, growing and stopping.
And now that's probably related to the resonances. You know, we certainly have hints of connections there, and that's actually something we plan to try to really work on, is try to elaborate. You know, if we could really understand the connections between the avalanches and the many-body resonances, I think there are connections that might really help. So that's
somehow your avalanche story does not take resonances into account.
The way I told it today. But
exactly.
We are in investigating it a little more carefully. What we found is the avalanche actually proceeds by resonances. That you have a system of length L, and it has all its eigenstates, and there are pairs of eigenstates that are strongly coupled by the Hamiltonian. And those are the ones which drive the avalanche. And it's not typical stuff. So that again has to do with probability distributions. So, but this is a story we just have hints of, and we're planning on looking at it more carefully. Also just for a technical reason, that the open system calculation, we have to diagonalize a super operator, whereas to look at the resonances, we only have to diagonalize the Hamiltonian, which is a problem. One is a matrix of 2 to the L by 2 to the L, and the other is 4 to the L by 4 to the L. Right. And so if you can get the physics you're looking for out of the eigenstates and the matrix elements, and you don't have to do the open system calculation, that would be a numerical advantage.
So you mentioned this crossover depends on L and T, of course, but would it also depend in any interesting way on the energy density? Like it might.
Oh, yes, absolutely.
So as I go to the edge of the energy spectrum, for example?
Yeah, right. Well, if you move away from the center of the spectrum towards the edges and the density of states are lower, all the MBL regions, the MBL regime, this pre-thermal MBL regime just grows and takes over the whole phase diagram. So the thermal phase shrinks, the MBL, I think just the pre-thermal MBL regime, although that's not clear, grows.
Right.
So moving away, moving to lower temperatures enhances localization, not surprising.
So I have a question for the short range or long range. So are there like more of a hand wavy, like, so when the interaction range is shorter and then we know the phase diagram, or it's like it's just specifically like nearest neighbor interaction?
No. Yeah, so I had this thing that the threshold is when the decay of the spin flip coupling is 2 to the minus 2r in dimension. So it corresponds to a certain decay length defined to be, this way. So this would be the relaxation rate. So this is in 1D at the critical point. The relaxation rate of a spin coupled to a bath at distance r, and the bath is big enough to relax it, decays this way, where r is measured by counting the spins. So the spins are spaced. The spins have density 1 on the line.
Okay,
sorry.
so
did I answer your question? I forgot what your question was.
Oh yeah, it's just we for the phase diagram, it's like you mentioned about the short enough range interaction.
So if you have spin flip interactions which decay any slower than this, so when I say short range, I mean exponential or faster, and if it's simple exponential, it has to be at least this fast, right?
Okay.
So if it's any kind of stretched exponential, that's long range for this purpose. And any power law is long range. For this purpose.
Okay, so it can
But
have.
that's, that's for the, in principle, is there an MBL phase which is truly stable? This crossover isn't going to really care about any of that stuff, right? This crossover from here to here, this is present with long range interactions. It's present in higher dimensions.
Okay, so it can have have a tail, but then it's like not a very long tail or not
The
very.
tail has to decay this fast or faster.
Okay, cool.
It's
Thank
pretty
you.
strict.
Thank you.
Sorry, question. So I have a question regarding L bits. So on the far left of the phase diagram, you have well-defined L bits, and on the far right, you don't have L bits. Let's say you're at a finite, you're given a finite L and T. What's the main mechanism? I mean, that actually makes you lose the L bits structure.
Well, if you're here and you diagonalize a given sample and look for L bits, you can find quite nice L bits, and they're quite well localized in that sample. But then as you go to larger and larger samples, you find, oh, they're getting less and less localized. And we believe that if you could go to an infinite sample, you will just no longer be able to make localized L bits if you're here. In some sense, really defining the L bits precisely, that's some sense an infinite time task, right? But if you have an exactly diagonalized system, there are means to define the L bits, right? And a number of people have worked on this and actually made constructions of the L bits for many samples and looked at the statistics of what they get. And you do find that as you do larger and larger samples, they get less and less localized because they're typically working in this regime here, right? A lot of the work on NBL, since this was viewed as the transition, a lot of the work on NBL, they never thought to go super deep in the phase because they thought, the transition's way up here, right? It's only recently that it's become, people are really saying, oh, the actual transition is quite deep, and this regime isn't really the NBL phase, it's just this transient thing. And that's I'm saying that, I think that a lot of people in the field aren't necessarily accepting that yet. And then there's other people who say in 1D, there's no NBL phase. So other people have made arguments, which I don't understand that they're of any substance yet, but that this phase doesn't even exist in 1D. Which is possible because Embry's work isn't a proof. He had to make a certain assumption which he couldn't prove. So there really is no proof that this is non-zero.
Great. So I think we are approaching the time for the other lecture that is at 4. So thanks, David. Thank you so much please keep your questions for tomorrow.
Yeah. Am I going to get a T-shirt?
Leo.
Not this year.
No T-shirts this year?
But we promise we will try to do.
David, I can send you a T-shirt.
I gave my previous T-shirt to my son, and it's one of his favorite shirts. And he's always asking me, "Oh, I want another one." I say, "But not this year." Okay, too bad.
I can get him a T-shirt, but not a Boulder Summer School T-shirt.
No, I want a real one. If you could get me another one, do you have old ones from previous years?
Leo has a Sharpie. He could probably write on the white T-shirt or something.
Yeah, exactly.
Maybe we can.
Authentic and you.
Do you have a collection of the old ones, Leo, that are sitting in a closet somewhere that aren't used?
Yeah. Well, I mean, they're used by me, but I certainly don't have.
You're wearing.
I'll look around. I wear them. Yeah.
Okay. Well,
and I'm a little short. I'm a little shorter than you and your son.
Yeah, maybe I'll have my son take a picture of the one he likes, and I'll send
sure.
it to you.
Sounds good. Yeah, send me a picture. I'll see what I can do.
If I remember.
Thank you.